So question 16, potential fault current, or PFC, is referring to how much current would actually flow if there was a fault. So we're talking about short circuit fault, and we're going to have either a short circuit, live to neutral, live to earth, or there's one other one, and that's going to be phase to phase. Because if you've got phase to phase, you're now talking about 400 volts. So proportionately, 400 volts is almost double 230 volts. So you're going to get double the amount of current flowing. So if you come up to a three-phase circuit, you know that your PFC is going to be between phase to phase. Of course, all these voltages originate from the supply company's transformer. So we've got our live, which is 230 volts, to neutral, or 230 volts to earth. And earth and neutral originate from the same point of the transformer. So between wherever our voltages are, there could be multiple fuses through different distribution boards to get this point. The earth and the neutral will always be continuous though. The neutral could be switched, providing it's switched at the same time as the live. Earth is never switched. The neutral can go through what we call neutral bars or neutral links, but it should always be connected unless there's some sort of testing going on. So let's imagine we've got a short circuit live to neutral. If we were saying that is 0.1 ohm and that is 0.1 ohm, you've got overall resistance of that circuit is going to be 0.2 of an ohm. So the potential fault current, you'll know, will be a massive 1150 amps. Simple Ohm's law. But if your fault was to earth, so you had a fault between there and there, and let's say the earth was only 0.05 ohms, then guess what? Because the resistance is now so much smaller, the lower the resistance, the more the current's going to flow. So it's actually 1533 amps. So in this instance, when you're looking where is your biggest fault current going to be, it's actually between live and earth. If it was a three-phase system though, so your fault is now between that phase and that phase, then it should be the same cables, three-phase cables, so the resistance to that you'd expect to be 0.1 ohm as well. So you've now got the same resistance, 0.1 plus 0.1 is 0.2, but you've got 400 volts now, so you're talking about 400 over 0.2 equals 2000 amps. So your biggest fault current is going to be phase to phase on this circuit. Now this for 2000 amps we're talking about here, or the 1150, 1533, whatever, you've got to make sure that your circuit protecting device, your MCB, will have a rating on it, and it's going to be in amps. So it's going to be, this is 10,000 amps, so it could be 10 kV, 10 kVA. That is going to say that this, if there is a short circuit, this MCB can actually trip without being damaged, because that's a hell of a lot of current. So you don't want the contacts welding together or failing at a time and welding shut. So that's what your kVA rating is all about.